Hello everyone, my name is Manan Gupta and thanks for joining in my talk today on load balancing and handover optimization in mobile multi-band networks. A typical cellular operator today owns licenses to multiple sub-6 GHz frequencies ranging from 700 MHz to up to 5 GHz, which is aside from what they might have in the millimeter wave spectrum. But for this talk, we will focus only on the sub-6 frequencies. While the lower frequencies offer a more favorable propagation environment, the higher frequencies offer more bandwidth and thus can support higher data rates. This frequency diversity, when coupled with user mobility and other sources of network heterogeneity, for example, power diversity, make it difficult to have a simple base station association rule. To address this, in this work, we propose a reinforcement learning framework for band selection and base station association in a multi-band network where our target is to have a balanced distribution of users across frequency bands and base stations. Let us now have a look at the network model. In this work, a base station is characterized by its physical location and the frequency band it operates in. The almost overlapping base stations in the figure depict a physical cellular tower which can support communication on multiple frequency bands. The network is modeled as a slotted time system where each user is associated to a parent base station. During the measurement gaps, a user measures the SINR from its neighboring base stations and reports it back to the parent, which then forwards it to the central controller along with the base station load. The central controller processes this information and returns the association indicators Xij. The users update their association according to the new Xijs. Handovers take place, data transmission takes place, and in the next time slot, the same process repeats. The throughput is defined as the Shannon rate normalized by the base station load and the fraction of time in a time slot the user dedicates to data transmission. For the presented network model, this is the base station association optimization problem where the objective is to maximize the log utility over time so as to have a fair rate distribution across users. This is a combinatorial problem because the association indicators have an integer constraint, which when combined with the outer summation over T results in a large search space. Even if we can work around the computational complexity, the problem is still not practically feasible because the handover interruption times are not known a priori. Due to these reasons, we formulate the handover optimization as a sequential decision-making problem and model it as a Markov decision process as shown here. The objective is to maximize the expected cumulative reward where the discount factor gamma is close to 1. Note that for gamma equal to 1, we could recover the optimization objective on the previous slide. We model the central controller as a neural network and process each user independently. This implies that the neural network architecture is independent of the number of users in the network. We empower the neural network with memory by introducing an LSTM layer, which allows the central controller to make decisions based on the history of SINR measurements and have dynamic cell boundaries. To simulate the wireless environment, we use the Quadriga package, which has two major advantages. First, the channel models and parameters are in alignment with the 3GPP standard. And secondly, it is capable of generating spatially consistent channel coefficients, which is very important for a mobility management study because it is essentially these correlations across space and time that we want to understand and exploit for an intelligent handover strategy. We compare the performance of the RL agent with the max SINR policy and the max receive power policy, which is denoted as max RSRP in the figure. We see that compared to the max SINR policy, the median throughput improves by about 35% and the throughput of the 20th percentile improves by 54%, with a slight throughput degradation for the 90th percentile. These observations are in alignment with the properties of the log utility function, which favors supporting weak users over the users which already have good channels. With that, I conclude my talk. Thank you for attending my presentation.